Hello, friends. Welcome to the online practical sessions of digital communication. Guys, today we are going to see study of delta modulation and adaptive delta modulation. As we know, guys, that in pulse code modulation, since we are going to transmit a many bits per sample, so due to which the signaling rate and the bandwidth requirement is much larger. So in order to compensate that, we are going to use delta modulation. In delta modulation, we are going to transmit only one bit per sample. So due to which the signaling rate and the bandwidth requirement is much lower as compared to your pulse code modulation. So let's start, guys. We are going to today see the study of delta modulation as well as adaptive delta modulations. So let's see first delta modulation. Now apparatus that we required is a Syntec kit, CRO and their probes and power supply. Delta modulation is a system of digital modulation which is developed after pulse code modulation. In this system, guys, at each sampling time, suppose the kth sampling time, the difference between the sample value at the sampling time k and the sample value at the previous sampling rate, that is k minus 1, it is encoded into just a single bit. So at each sampling time, we ask a simple question that has that signal amplitude, it has increased or decreased since the last sample was taken. So guys, if the signal amplitude it has increased, then the modulator's output it is at logic level 1. Similarly, if the signal amplitude it has decreased, then the modulator output it is at logic level 0. And hence the output from the modulator, it is a series of zeros and 1, which indicates what? Rise and fall of the waveform since the previous value. Now, you can see the arrangement that is of delta modulator at and demodulator at figure 1 and 2. So this is, guys, figure number 1. So let us understand that how this delta modulator it is going to work. Now the analog signal which is to be encoded is into what digital data is applied to what this positive input of this voltage comparator, and which compares it with the signal applied to this negative terminal, negative input from the integrator output. Now this comparator output, guys, it is a logic 0 or it could be logic 1 depending on whether the input signal at positive terminal is lower or greater than this negative terminal input signal. Then the output, the comparator output, it is latched into a D flip-flop. So guys, now I am going to explain you the theory part of this modulator and demodulator. So at the time of practical, we will just see the practical. The theory part I am going to cover it right now. Now, since the output of this comparator output, it is latched into this D flip-flop, and which is clocked by the transmitter clock. Now the output of this D flip-flop, you can see it is latched to 1 or 0, with this synchronous with the transmitter clock edge. And then this binary data, that is 0 and 1, it is transmitted to the receiver. So, and before that, the output of this bistable circuit, that is a D flip-flop, it is converted to unipolar to bipolar converter. And the output of unipolar to bipolar converter, it has been given to integrator. Now understand this receiver. The output of delta modulator that is being transmitted is given to this receiver section, and which is also fed to this D flip-flop. The output, the data input, it is latched to what? D flip-flop, and which is clocked by this receiver clock. And output of this bistable circuit is given to what? Unipolar to bipolar converter. And this block, it is going to convert, remember this block, it is going to convert a logic 0 to voltage level +4 and logic 1 to voltage level -4. And then this bipolar output is applied to this integrator. So whose output, the output of this integrator, it could be a rising linear ramp signal when -4 is applied to it, that is corresponding to binary 1. And second, the output of this integrator, it could be what? Falling linear ramp signal. It is like this one, falling, and this one, it is what? Rising. So falling linear ramp signal, when +4 is applied to it, that is corresponding to what? 0, binary 0. And then this output of this integrator, it is given to what? It is given to low pass filter. Now guys, and this low pass filter, that would be your Butterworth fourth order low pass filter. At the output, we would get the analog output that we transmitted. Now guys, let us understand the working of modulator, with the help of this waveform now. Now suppose guys, at instant t equal to 0, this is at instant t equal to what? 0. The integrator output, see, this is the integrator output. The ramp signal that you are going to see on the screen, it is your integrator output. Now, the integrator output voltage, you can see it over here. The integrator output voltage, it is lower than this analog input. See, this is your analog input, and this ramp signal, it is your integrator output. Now at t equal to 0, at this instant, we are going to find that integrator output, this is the integrator output, it is lower than the analog input. Then this causes the voltage comparator, voltage to go high, that is logic 1. Then this data, it is latched in the what? D flip-flop at the rising edge of the transmitter clock. This is the transmitter clock, and this is a rising edge, and this is a falling edge. So we are going to latch it at the rising edge of the transmitter clock. Then the latched one output of this D flip-flop is translated to -4 volt by unipolar to bipolar converter block. And then integrator then ramps up. See, you can see the integrator, it is going to ramp up to catch your analog signal. Now, at the next clock cycle, see, this is the next clock cycle. So you will find at this next clock cycle, the output of this integrator, it is more than that of your analog input signal, right? So a 0 is latched into a D flip-flop. See, it is a 0. Now the integrator now ramps downward. See, it is going to move downward as plus 4 voltage signal from unipolar to bipolar converter appears at the input. And again, this ramp signal, it is tries to catch your analog input signal. So you can observe it at the several clock pulses. This integrator output, it is an approximation. What it is? It is an approximation of your analog input, which tries to catch this analog signal at each sample time. And that then this the data stream from this, data D flip flop. It is nothing but your what? Data output. That is a delta modulator output. So hope so you understood that how this, the data output it is being transmitted. Now at the demodulator, what is going to be happen then? As we know, as we already seen that demodulator, it consists of what? Your D flip flop, it is there. Your unipolar to bipolar converter, which is followed by this integrator and low pass filter. Then this delta modulator, demodulator, it is going to receive the data from this D flip flop of your delta modulator. Then it is going to latches this data at the every rising edge of this receiver clock. See, this is the receiver clock, and which is, it is delayed. This receiver clock, it is delayed by half clock period for the information with respect to transmitter clock, uh, right? So this has been done so that the data from the transmitter, may settle down before being latched into the receiver flip flop. Now, as we understood this theory by means of this block diagram as well as this waveform, now let's understand the connection diagram of the flip flop. Now this is the delta modulator and adaptive delta modulator kit, and it has, now we are going to explain, we will come to know what are the different blocks are involved in your delta modulation and adaptive delta modulation. Now guys, this is the function generator. This section is your function generator. So this function generator, it is going to produce a different, waves of variable amplitude at different frequencies: DC 250 hertz, 500 hertz, 1 kilohertz, 2 kilohertz, like that one. This section, this above section, it is a transmitter, guys. That is called, a delta modulator section. So this is your transmitter section. As the clock frequency, you can observe it. This is the clock frequency, clock generator. And remember, and this is your sampling frequency. So sampling frequency, this is a selector switch. By wearing your selector switch, you can select the sampling frequency which is available at 32 kilohertz if both the inputs are 0, 0, 1, then 64 kilohertz. For 1, 0, it is 120 kilohertz. And then for double 1, it is what? 256 kilohertz. Now this is the guys, this comparator that we studied in this now, the block diagram. So what we are going to do it, we are going to connect this analog input to this positive input of this comparator. One by one, step by step, guys, we are going to, I'll show you the connection, that how we are going to do the connection. And if you will observe, the output of comparator is given to this data input of this bistable circuit. This is nothing but your D flip-flop. And then output of this D flip-flop, it is internally connected to unipolar to bipolar converter. And then output of this bipolar is converted into your integrator. And if you will observe it, this switch, we have to move towards the left hand side. And this integrator, it has a 4 gain, standard gain, which is then multiply by 2, multiply by 4, multiply by 8, like that one. So depending on this operation of this switch. And this section, guys, it is your adaptive control circuitry. In order to perform the practical of ADM, we are going to use this section also. But right now we are going to see the delta modulation. After that, guys, what we have to do it. When the data output it is present, we have to connect it to the receiver section. You can see it. This is your receiver section. The lower section, it is your receiver section. It is there. This is your bistable circuit, unipolar to bipolar converter, which is followed by this integrator. Again, at the receiver, we have this adjustable gain for delta modulation. And for delta modulation, this switch position, it should be moved towards this right hand side. And the output of integrator would be given to this 4th order Butterworth low pass filter. And at the output, we would get the input signal that we transmitted. So now let's, guys, one by one, we are going to see that how we have done the connection. Now, what I told that this is the input. So we have taken the input from the test point, that is of 1 kilohertz signal. After this, we have to connect this 1 kilohertz signal to this input of this comparator, that is a positive input, positive terminal of this comparator. After that, guys, see, this is your transmitter clock generator that we have to given to this clock input of bistable circuit. So see, we have connected this input to this clock input of this bistable circuit. After that, the output of this comparator, we have connected to this input of your bistable circuit, that is your D flip-flop, because we need to latch the output of this comparator to this. After that, guys, since output, this is a DM output, it is internally connected to unipolar to bipolar converter. So the output of unipolar to bipolar converter, it has been given to the input of your integrator. And then the output of this integrator, we need to connect to this negative input of this comparator. But before that, I have taken the picture of this selector switch. See that it is the selector switch, that is a gain control, and this switch position, it should be towards the left of the transmitter section. So by means of varying the gain, you can see the waveform. After this, guys, see, by this red cord, we have connected the output of integrator to the negative input of your comparator. So this is the connection diagram of your delta modulation, guys. Now, guys, what we will do it, we are going to connect the input. We are going to observe the input on this CRO. So we have connected this test point at pin number 9 by channel 1 on channel 1 of the CRO, and you can observe the waveform. See, this is your analog input signal, which is of 1 kilohertz available at your test number point 9. After this, guys, now this is the output of your delta modulator, which is in the form of your binary 0 and 1, that is a 1 bit. Now we are going to observe this DM output on CRO. So I have connected to this second channel of your CRO. So see, you can see it to the second channel of the CRO. I have connected this probe, CRO probe, and this is the output of your delta modulator in the form of your 0, 1 and 0, like this. Now guys, we are going to compare, we are going to see the input analog wave and the output of this bistable circuit, as well as you can also compare the main thing it is guide in this practical. You have to compare the input signal and your analog and your comparator output. So this pin number 10, it is your comparator output, that is a negative terminal input of this comparator, and this is your pin number 9, test point 9. So we are going to now compare the input wave, analog wave, and the integrator output. See the ramp signal, how the step size, it is a fixed, the gain it has been fixed, and how it is going to catch this your analog input signal. So this is the another view. And as we know that this is the output of your delta modulator. Now guys, the next point it is that this is a transmitter section, guys, and this data modulator output, it is being transmitted and it is received by this receiver section. So you can see that we are going to connect this data output, that is a DM output, to this data input of bistable circuit D flip flop of the receiver. Now, since it is clocked by this clock pulse, so we need to connect this receiver clock pulse to this clock input of bistable circuit. Next point is that, as we know, the output of this bistable circuit is internally connected to the unipolar to bipolar converter of the receiver. Now the output of this bipolar converter is connected to the input of this integrator, and this is the selector switch by which you can get the multiple gains, and this selector switch, it should be moved to the right hand side, as I already told. Now the output of this integrator is connected to this Butterworth low pass filter, so we have connected to this, and we are going to compare the output of this low pass filter received signal and this transmitted signal. So you can observe this waveform, guys. Say this one, it is your input wave, transmitted wave, input analog wave, and this signal, it is your received signal, that is the output of this low pass filter. Now this view, it is a more, you would get a clear idea of this one. Upper one, above one, it is your analog signal, and lower one, it is your output of your low pass filter. And this is the selector switch of your receiver by which you can vary the gain. See, if you are going to increasing the gain, how it is going to clearly catch your input signal. See, like this one. And if the gain it is being low, then how the output it is being distorted. The shape it is not resemble to this input signal. So hence you can vary this one and observe the waveform, guys. Now guys, we will see the practical, that hardware implementation. So guys, this is a function generator. As already told, 250 Hz, 500 Hz, 2 kHz, 1 kHz signals are there. So let us connect at 1 kHz signal and we will check this signal on CRO. We have connected to this ground and this is your input signal. After this input signal, we are given to the pin number 9, it has been written over here, that is your input. So I am going to connect it over here. Then The second input of this comparator, it is coming from the output, but we will go in this manner. Now this is output of your comparator. So the output of a comparator, it has been latched by this D-type flip-flop, and we have connected to the data input, that is a pin number 12, like this. And guys, this is your DM output, that is data output. So what is being, this data output is internally connected to this unipolar to bipolar converter, because output is unipolar. So output now, it is unipolar to bipolar converter. So we are going to connect this output of this converter to the input of this integrator, that is a pin number 16, like this one. Now the output of this integrator, we have to connect it to what? This second input of comparator. But first we will check the output of integrator, that how it looks. But before that, what we will do it, see, this is a clock input of this D flip-flop, that is a bistable circuit, and this is a clock generator circuitry, it is there. So we are going to connect this clock, and you can see the selector switch are there. So by which you can connect it to 32 kilohertz, 01 in the 64 kilohertz, 10 means 120 kilohertz, 128 kilohertz, and 11 means 256 kilohertz. So now we are going to connect this clock generator to the clock input of this D flip-flop, that is your bistable circuit. After that, this is the output of the integrator. Now first we will check the output of this integrator on your CRO, and then we are going to connect it to the pin number 10, that is a negative input of your comparator. So let's see the output. So this is the output of the integrator. Now I am going to connect the output of this integrator to the negative terminal of this comparator. So now we are going to observe the output of your DM wave, that is delta modulation wave. Now we are observing the output of your this data output, that is a DM wave on your CR. So this is the output, that is a data output. Now guys, we are going to observe the input wave, that is your 1 kilohertz signal on CRO, as well as the output of the integrator. It means how the output of integrator, it is going to approach the input signal. So now we are going to connect, that is a first channel of the CRO to the input waveform, that is at pin number 9, that is a positive terminal of this comparator. Now the second channel of the CRO, I am going to connect it to the output of the integrator, that is pin number 17, that is connected to pin number 10 input. So we can connect it over here, and let's make it connected to the ground. You can see the channel 1 waveform, that is this waveform, sinusoidal waveform, it is your input signal, and the second channel output, it is your output of your integrator. So you can observe it how this integrator, it is output, it is going to catch your input signal. As we know in DM, the step size, it is constant, the rate of rising of that ramp signal, it is what? Constant. So it is you can compare the output of the input and your integrator output. We can also compare the output of this, that is your data input, that is the output of this comparator we have connected to this D flip-flop. So we are going to observe the clock signal, which is right now at 32 kilohertz, and this is the output of your comparator. We are going to observe the waveform on the CRO. So above one, it is your data output, and this is your clock input. You can observe it over here, that is a 32 kilohertz. can observe again the output of this bistable circuit, that is which is going to give you the data output, the output of delta modulator. Now guys, this is the output waveform that we transmitted. So you can see this one, this output. Now this is a transmitter section. Now this is your receiver section. So now we are going to receive this signal and we want to make it to receive our original signal that we transmitted, this one. So I am going to connect the data output of the transmitter to this receiver section, to the bistable circuit. Data input at pin number 13, I am going to connect it over here. Now since it has a clock input and this section it is a receiver clock output, so I am going to connect the receiver clock output, which is right now it is 32 kilohertz. It is connected to your clock input. Now you can find this, the output of this bistable circuit, it is connected to the unipolar to bipolar converter. So internally it is being connected. Now the output of bipolar converter, output of this bipolar converter, now I am going to connect it to the what? Input of this integrator. So this is the input of integrator, and these are the guys selector switch. So you can move it towards the right side because we are going to use a delta modulation, that is again it is fixed over here. So now we are going to observe the output of the integrator, whether we are getting it or not. If we'll get the output, then we can connect it to those low pass filter in order to recover the signal. So guys, we are now observing the output of this integrator to the CRO, that ramp signal it should be generated. So it is the output of your integrator. Now guys, now just we observe the waveform of the integrator. If you want to observe the waveform of this bistable circuit, unipolar to bipolar circuit, we can also do it. So we can observe the output of this bistable circuit. Let's connect it to the ground and see, this is the output of your bistable circuit. It is there at the receiver section, guys. So this is the output of the DM that we transmitted and it is received at the receiver. The output of the integrator, it has been given to this Butterworth low pass filter, that is pin number 50. It is the input. Now we are going to observe the output of your low pass filter. This is the output of low pass filter. Now we are going to observe the input wave that we transmitted and the receive wave, that how it is going to be received. So guys, as we have to compare this waveform, so what I am going to do it, I am going to connect the input waveform. This is my transmitter section, input waveform at pin number 9. And since we have to observe the output waveform that is being received at the low pass filter, so it is connected to this output of low pass filter and we have connected this ground. Now we are going to compare the output of your input and received output wave. Now guys, the upper wave, this one, it is your input wave, and the second channel, it is going to show you the output wave. So you can observe it, the output of the low pass filter, how it is similar to your input filter, but you can also control the gain. Since it is a delta modulation, gain it is fixed. So at the different gain we can show the output. So if I am going to change the gain, this is the selector switch of the gain at the receiver section. If I am going to change it to the 0 1, that it means the gain it has been increased. So you can observe the waveform over here. See now this lower waveform, that is the output of your low pass filter, how it is getting closer to the input waveform. See, this is the effect of changing the gain. You can observe it, how it is being distorted. If the gain it is not properly, it has been set. So guys, it is all about the output of your study of your DM system. So now guys, we are going to see the advantages of your data modulation system is very simple to implement it, also very cheap, cost effective. And since single bit encoding we are going to use, which is going to increase the sampling rate and to transmit more information at some sampling rate for a given system bandwidth. But unfortunately, guys, that the practical use of delta modulation is limited due to this following factors as like your noise. As noise, it is unwanted, unpredictable, random waveform which is accompanying the information signal. So whenever the signal it is received by the communication medium, it is always accompanied by noise. Then your distortion. It means the output waveform, it is not exactly the true copy of the analog signal. Since in study, just we have seen the practical, we have studied the kit, on the kit we have done, but in real time applications, if we are going to transmit it, the transmission medium in that, there is a lot of possibilities of the noise. And next, guys, that we studied in our theory, that is your slope, overload noise, and granular noise. That is the rate of change of input is when it is very, very high, then the output, the integrator output, it can't, match up to the input signal due to the limited, fixed step size. So due to which it could not approach that one. So there is a huge gap and slope overload noise occurs. And last is granular noise. If the rate of change of signal rate is very, very low, then the oscillation of the integrator output it is going to take place on that one. So due to these are the drawbacks which makes us to study, adaptive delta modulation. So guys, thus we studied, delta modulation, that how this delta modulation it is being generated, how the 1 bit per sample it is going to be transmitted and at the receiver by means of your bistable circuit, then unipolar to bipolar converter, integrator, and last at the connecting to the low pass filter. Thus we received the your signal that we transmitted, and how we have seen that the if we are going to keep the gain constant, that how would be the output, and by changing the gain how the distortion it is going to take place. So it is very, very necessary to properly setting the gain or at the transmitter as well as at your receiver size. So thank you guys, it is about your delta modulation system.